Yeah, thanks everyone for inviting me. So yeah, as Giovanni already announced, the title of my talk is going to be Machine Learning and Physics, Bridging the Gap. And in some sense, this is going to be a sort of unusual contribution to this conference, because even though I started in condensed matter physics as a PhD student with Achim Rosch, I actually transitioned out of physics into machine learning, and this has been actually a while ago. While my research is still strongly inspired by my physics background, and hopefully what you will learn here in this talk is, since my understanding it's kind of a lot of theorists here also, how can actually ideas from theoretical physics improve machine learning algorithms? And if we have time in the very end, I might also talk still about applications of machine learning methods within physics. So let me maybe just get started. Okay. So the goal of machine learning very broadly is to understand complex data sets, right? And this can be from multiple domains. It can be understanding, galaxies and distinguishing galaxies from stars in the universe. It could be classifying collision events in the Large Hadron Collider, generating molecules more efficiently to kind of explore the large search space and potentially coming up with new drugs, or understanding complicated materials. So what I kind of decided to do in this talk is the following two things. In part one, I will essentially start with an introduction to probabilistic modeling and Bayesian inference. So I kind of assume that this is novel to the physics audience to some degree, but it's actually really important and good to know about. And then I will talk about my kind of special area within probabilistic modeling, which is an approximation scheme. It's called variational inference, which has become very popular in the recent years and really allow you to scale up probabilistic modeling and combining it with deep learning and kind of apply it in very large data sets. And I will also tell you how this method in particular was inspired by theoretical physics about 20 years ago, and how physics ideas can still help improving variational methods. And then in the second part, I decided on a kind of fun project, which is published in the International Conference of Machine Learning 2 years ago. And it's really an application where spontaneous symmetry breaking, so a kind of a rather involved concept from theoretical physics, actually appears in certain time series models for language. So kind of totally out of their classical context. And I will provide you with some details how it works, and how it actually leads to optimization problems there, and a new algorithm that we proposed, which is inspired on the idea of Goldstone modes, and which we then called Goldstone gradient descent. So this is pretty much what I'll try to cover in the next half hour or less. So let me get started. So I assume not everyone is familiar, but maybe a fraction of you is familiar with the idea of Bayesian inference. So Bayesian inference is a branch of statistics. So there's frequentist statistics and there's Bayesian statistics. And Bayesians care about so-called probabilistic models of the world. So what is a probabilistic model? It is actually a joint distribution over data points X that you observe, and certain parameters, or sometimes also called latent variables, that you don't observe, right? I mean, those could be, for example, low-dimensional explanations of the data that you observe. And usually the joint distribution P of x comma theta factors into what's called a likelihood, P of x given theta, so in other words, the probability of the data given that you know these latent variables or parameters, times P of theta, which is a prior distribution. In other words, a distribution that expresses your prior belief over those values that theta can take, maybe constraining them into a subspace of your parameter space. And the object of interest is to kind of narrow down the distribution of these latent variables or parameters. And that's called the Bayesian posterior, P of theta given x. And it's really just the product of the likelihood times the prior, but normalized such that that distribution really integrates to 1, right? So I'm kind of dividing by the integral over the product of likelihood and prior. And the picture, and the picture that you should have in mind in a very simple toy setup is as follows. So imagine you're kind of working with all Gaussian distributions. So then you're kind of making observations of data that you assume come from a Gaussian distribution with unknown mean. So then the prior distribution could be this kind of very broad, highly entropic blue dashed distribution over parameters that constrains your search space somewhat. Then you make an observation, and that leads to that likelihood curve, which is also a Gaussian, not necessarily normalized as a function of theta. And then the posterior is just the product of the two. And you see that the mean of the parameters kind of interpolates nicely between your prior belief over the mean and the observation. So you can think of that as a type of regularization, right? At the same time, with more observations, your posterior narrows down and gets more and more sharp. And that means that as you observe more data, your belief over parameters gets more and more refined and constrained. So there are many examples of where probabilistic models appear in the real world. So let me just kind of pick two examples which are somewhat relevant to my work and also that will be relevant here in this talk. So I'm mostly concerned with combining probabilistic models with deep learning because this is just a relatively powerful combination and and applies to many setups. And the two models that I want to highlight here are one, deep generative models for example, visual data. So there's this, the famous variational autoencoder that some of you might have heard of is a probabilistic model that essentially consists of a low-dimensional noise variable z. So this is my latent variable. And the generative process is, or the likelihood is just taking that noise and pushing it through a trained neural network with parameters theta such that I result in a highly structured object like an image, right? And then the challenge will be actually how to train or how to actually learn these model parameters theta. And you'll learn that this involves, for example, variational inference for training. Right? It's not a simple supervised learning problem. It's an unsupervised learning problem. And we sort of have to do something slightly more sophisticated. At the same time, there are also these other models which are popular in machine learning and in natural language understanding. So those are so-called word embedding models. So they kind of associate words with abstract meanings in a so-called semantic space, such that you can then actually make a plot of all the word embeddings and kind of measure their semantic distances and relationships by investigating the clustering structure of this word embedding cloud. So this is another example of a Bayesian probabilistic model. And of course, there are endlessly many more. Pretty much every machine learning model can be formulated as a probabilistic model, or at least a large class of them. Okay. So why is it difficult? Why is it a challenging research to actually learn or improve? Why do we actually care about algorithm improvement in this space? Well, it turns out that computing the exact posterior, in other words, p of theta given x, is actually an incredibly hard problem. And the reason is why it's hard is that you actually need to compute its normalization constant, which I denoted as p of x. In other words, I take the joint distribution over parameters and data, and I integrate over all possible parameter values. Now, as a physicist, this reminds us very much of a partition function, right? Where p over parameter, where essentially x are just some fixed entries, but the parameter space is really characterized by theta. And we all know as physicists that computing partition functions in high dimensions is very hard. So even numerical integration is infeasible. Think of billions or even billions of parameters in neural networks that you have to integrate out. And also sampling-based methods, such as Markov chain Monte Carlo methods, they sometimes apply, but in general, they're really slow to equilibrate, right? And so we want to kind of come up with very different, fundamentally new way of learning these kinds of models. And as I already said, I'll mostly work on variational inference, variational methods. So this is what this talk is mainly going to be about. So optimization-based inference. Okay. So what is then the idea of variational inference? It's actually to take a simpler distribution, for example, a Gaussian distribution, to approximate a more complicated distribution. In other words, the posterior. So the toy example that you all should have in mind here, let the posterior be this black object, like this bimodal, more complicated distribution, and we approximate it by a simpler distribution as well as we can by changing that red distribution's parameters, which in this case are the mean and the variance. Right? So lambda are our variational parameters. And the measure of doing so is we're actually minimizing an information theoretical measure of distance between functions, which is called the Kullback-Leibler divergence. And you'll see shortly what that means. So this is actually the objective function that you minimize in variational inference. So you have your probabilistic model, which is again characterized by your joint distribution over parameters theta and x, so p of x comma theta. And you take an expectation of that object with respect to q, your variational distribution. So this is called an energy term because it's really sort of if you think of the whole thing as a free energy, which corresponds to energy and entropy at temperature 1, this term would have the correspondence of an energy. But then there's also the entropy term, and you'll shortly see why both terms are important. So note that here temperature is set to 1 because it doesn't naturally appear in variational inference. So what happens if I kind of optimize these two terms separately from each other? If I only care about the energy term, and there's no entropy penalty, so then you can easily convince yourself that you will essentially collapse to temperature 0, and that means your variational distribution is just a point mass that places all of its probability at the maximum likelihood mode of the joint distribution. In other words, you only care about explaining the data, you don't care about the associated uncertainty. But I mean, if you then also add the entropy term, then these two terms magically conspire, and you kind of get this nice matching between these two distributions. Okay. So I worked on a bunch of ways of improving these variational methods, and a very simple one is what we call variational tempering or deterministic annealing. So the idea is very simple. So oftentimes, your evidence lower bound that you're trying to optimize is actually a non-convex optimization function shown on the left-hand side. So there could be, as a function of two parameters, for example, there could be a good global optimum, which is denoted as the red dot, and there could be a poor local optimum that you're trying to avoid. If you don't do tempering, you will either deterministically find the correct answer or the wrong answer. But if you introduce an artificial temperature and slowly ramp it down, you'll actually see that the entropy term is concave, and so it kind of makes the optimization problem easier. And then if you slowly dial down temperature as you optimize, you'll be guided into the good solution, right? And of course, in high dimension, everything is much more difficult, but you'll see that pretty much every time you find a better local optima than if you wouldn't do annealing. And actually what the paper really is about is to kind of do this adaptively on a per data point level, and this is probably too much for here. There's also another interesting project that we published at another top machine learning conference, NeurIPS, in 2019, and that actually relates to another concept that physicists are pretty familiar with, namely perturbation theory. And again, to that you need to kind of understand the connection to free energies and physics a little bit more. So remember what the posterior normalization constant that we cared about, that we couldn't compute, was called P of x. And that can be actually written as an expectation under a certain distribution Q, think of a variational distribution, and then of essentially the ratio of the joint distribution divided by Q. And I can exponentiate that ratio and take the logarithm. So I write it as E of log P minus log Q. Right? So this is just P of x. And now everything that's highlighted in green here, I call V, and I call it the interaction energy. It's essentially the difference between the true energy and the variational energy. So now I can actually show that if I do a Taylor series expansion around a certain expansion point V naught, and I only do odd orders of expansion, and I pull out a certain factor, that this is actually a lower bound to this object P of x. Right? And that's actually important because usually in physics we don't care if if a perturbative expansion is a lower bound or not, but in optimization we do, because only if something is a lower bound of something else we can safely optimize it and not run the danger that we kind of run into infinities and get some weird solutions, right? And so this is sort of a systematic way, by adding essentially these higher order Taylor expansion terms, we showed that we can close the gap and kind of get better posterior approximations. And you can actually convince yourself that the regular evidence lower bound is corresponding to the first order Taylor approximation up to a constant, which you don't care about in optimization. Okay. So there's also like a third interesting project where physics intuition help you come up with new algorithms. So for example, a couple of years ago, we interpreted, as one of the first authors, we interpreted stochastic gradient descent, which you run when you optimize your deep learning algorithms, for example, as a diffusion process. And we were wondering not only what happens, how does this diffusion process actually converge to the optimum, but actually if I run it for a very long time, what is actually the sampling distribution that stochastic optimization converges to? And how can I actually characterize the shape of that distribution? How does it depend on various parameters like the learning rate? And so this is kind of the picture that you should have in mind here. So again, this is a two-dimensional parameter space. The red dot is kind of giving you the optimal solution that you're after in machine learning. The dashed line kind of is your true posterior. And then you see that if you pick the right learning rate, you can actually map that you can match the sampling distribution to the posterior, and you can effectively collect these samples of stochastic gradient descent as an approximation to a Bayesian version of the problem, right? So it's a very cheap way of obtaining samples from your posterior, and we kind of essentially derived all the criteria of how to pick the parameters correctly, such that you can misuse simple stochastic optimization as a cheap CMC sampling algorithm. Okay. So this kind of concludes the first part, where, again, as I said, this would be about giving you an introduction to Bayesian machine learning and probabilistic modeling, and how physics ideas can help with developing new algorithms in machine learning. So let me actually then also talk about my second part, which again is kind of a fun project where our physics backgrounds really helped us coming up with that observation. And this is actually largely due to Robert Bamler, who also is a PhD in physics, and who was actually my first postdoc, and who now just got a faculty position also in Tübingen in Germany. And the title of this paper was "Improving Optimizations for Optimization for Models with Continuous Symmetry Breaking." Right, so it's kind of really machine learning models, totally out of the scope of physics, but discovering that certain physics phenomena can actually occur also in these systems. And to understand this observation and this curious finding, I need to actually first explain a relatively simple but important machine learning model, namely probabilistic, or in general, matrix factorization. So what is matrix factorization? A matrix factorization model is, for example, used in your Netflix recommendations. Right? You oftentimes observe a large matrix X, which could be a click matrix, users clicking on movies. The problem oftentimes is that this observed data matrix is very sparse, because obviously you couldn't watch 10,000 different movies that are available on Netflix. But a recommendation system really cares about, if you were exposed to a given movie, would you actually like it or would you not like it, right? And so, and therefore, this quite naturally maps to a so-called matrix completion problem, where, again, you have a sparse, incomplete matrix X, and you want to kind of algorithmically somehow infer its missing unobserved values. And the way it's typically done is by a very simple assumption, namely that that this matrix actually exhibits a low rank structure that you want to learn. Right? In other words, that the matrix X here can be written as a product of kind of a tall matrix U and a wide matrix V that both have kind of a low rank structure. And then what you do in order to kind of match the product of U times V to X, in order to infer the missing elements, you're kind of, element-wise, you're kind of minimizing the squared L2 distance between these, between X and the corresponding product of U and V, and this then maps to an optimization problem over U and V that you can solve using, for example, gradient descent. Now, it's quite interesting if you think about it, and usually you don't care, but this problem actually has a rotation symmetry, right? I mean, if you take any rotation matrix R, a K by K matrix, where K is the rank of this low rank problem, then you can actually simultaneously rotate V, call it V prime, and you can also rotate U transpose from the right-hand side with R transpose. And actually it turns out that this is the original problem, and the loss function is exactly the same, right? So, so basically there's an entire manifold now of solutions which is parameterized by these rotation matrices R. And usually in machine learning you don't care, because you're happy with finding any solution, and so you usually don't encounter any problems with that. So to kind of give you one example of a probabilistic matrix factorization, I already talked about recommendation systems, but another popular model is word-to-vec. I already talked about these word embedding models, where you associate points in a latent space with individual words in such a way that these words reflect kind of the semantic meaning, and in such a way that neighborhoods contain essentially words of similar semantics, right? And these clusterings naturally appear when you also formulate word-to-vec or word embeddings as a matrix factorization problem. So so it's an unsupervised model for learning vector representations of words. The input is just some unstructured text collections, and the output are these word embeddings. And it's actually pretty much the same here if you think about it. I mean, if you would rotate all this entire cloud of word embeddings by a certain angle, nothing would really change. So there's really also this exact symmetry there, because only relative distances matter and not the absolute orientation of these word embeddings. Okay, so it's actually nice that one model that we came up with Robert Bamler that I mentioned before in 2017 is actually a time series extension of word embeddings. So in other words, this is now a model where you can make a movie of how words change their meaning over different years. So what you see here is the time span from the 1930s, and we're kind of monitoring the whole word cloud as it evolves. So this is actually trained on Google Books, like a very large corpus of digitally collected books that were kind of divided up into tiny sentence pieces so that we can actually use them for learning word embeddings. And what you see here is that the word broadcast, for example, makes an interesting evolution. Previously, it was surrounded by words such as distributed and scattered. So actually, this broadcast was kind of had an agricultural meaning. And then later on, it was associated with media technology. And you see that other words like radio and press become the nearest neighbors at the later half of the 1930s. So this is kind of this is the type of model that we were interested in and where we encountered this problem of spontaneous symmetry breaking. So let me formalize that a little bit more. So imagine you have sequential data from x1 through xt. So this could be data collected from historical books. Every t stamp corresponds to one time stamp. So for example, 1 year between the last 200 years. And then we also have sequential model parameters, namely z1 through zt, right? And so the z's here are our latent variables, and in this case, they are the word embeddings that essentially summarize language, or that summarize the core occurrence patterns that you observe in your text corpora. And then for this class of time series models, we actually have a loss function over these time-varying latent variables z1 through zt that decomposes into two terms. One is you have sort of an instantaneous loss. So you can think of a likelihood. So you model the words at time t conditioned on the word embedding z at time t, right? And now you're summing up all of these loss contributions. But you also have another term that couples all of these word embeddings together, right? And this is kind of really your modeling assumption that the language evolution really happened smoothly. So typically you have some sort of quadratic coupling that allows you to eliminate some of the noise that you would otherwise observe. And now the first term, this is the term that exhibits this rotational symmetry. So one way to write it again is the loss function when I insert a rotation matrix RT coming from rotation group SOD at time t, and I rotate my ZT, then this is just the same as the loss function of XT and ZT. And again, one way to think about the second term is some sort of quadratic regularization. So you're essentially penalizing that these parameters change too much as you go from one time step to the next one. So you're kind of taking the differences at consecutive times and squaring it up. So this is a simple quadratic penalty term. Yeah, and there are many examples. You've just seen one example is dynamic word embeddings, but you can also extend matrix factorizations to sequential setups. For example, if you make sequential movie recommendations, this is a pretty natural setup. So how much time do I actually have?
2 more minutes.
2 more minutes. Okay, so then I really have to wrap up. Okay, long story short, so this is the model class. There are interesting things that you can do with these language models. You can, it's a really relevant problem. You can kind of query what are the fastest moving words and so on. But let me actually go to the interesting physics and hopefully summarize it. You're all familiar with these kind of Mexican hat potentials. So this actually boils down to this optimization problem where you have this complicated Mexican hat in high dimensions. At early phases of gradient descent, you randomly initialize your algorithm, and then you actually quickly collapse into this valley, right? And this part of the gradient descent scheme is relatively fast. But then it takes a very long time until you find the global optimum, right? And this is because the symmetry breaking term can be thought of as a tiny tilt of this Mexican head potential. Let me see what's the most important slide here. Okay, so so if you think of the matrix factorization problem, and now we're kind of coloring these different matrices, the slices of the matrix as different colors, we can actually visualize what's going on. And basically, at some intermediate stages of your optimization, you kind of get embeddings structures in 3 dimensions, as you see here. So actually, the chain here corresponds to the time chain. And what you really want is that these chains contract to single points, right? Because only then your algorithm has converged. Long story short, you can make movies. Okay, so the way we solve the problem, sorry that I'm rushing here, is that essentially we're optimizing these 2 terms separately. One term is solved using gradient descent, and the other term is solved using an optimization in the symmetry direction, using elements from the corresponding Lie algebra that we then exponentiate. And so we're essentially carrying out an optimization in the curved space by actually carrying it out in the Lie algebra, and then exponentiating the corresponding parameters using the matrix exponential of the corresponding Lie algebra elements. Okay, yeah, I think I have to finish. So let me quickly sum up what kind of what a kind of nice application of this ultimately is. If you don't do that, your word embeddings will actually be twisted along the time chain, right? So if you don't care about this optimization problem, there will be sort of arbitrary twists of word embeddings that are some sort of unphysical or not expected. And if you then want to translate a modern word into its historical language, you will kind of end up in an arbitrarily rotated misspaced place. So for certain applications, we actually want to completely eliminate all of these rotations such that we can translate a modern word into a word from 1800. And for example, we can take the word car and translating it back 200 years, and then we look up the nearest neighbors at that year, and we report what we get. Let me just kind of finish this because it's kind of fun. So this is like a new application that was enabled by that. So if I take the word car and look up its word in its position in the year 1800, I get words like boat, saddle, and canoe. If I look at DNA in the year 1800, the closest nearest neighbors would be other chemical compounds. If I look at electricity, I get something like virus, friction, vapor. And most interestingly, if I look at tuberculosis, which is a term that wasn't coined before 1840, and I look up the nearest neighbors in 1800, I get essentially the symptoms like vomiting and so on. Again, this was only possible using this kind of enhanced optimization scheme that was inspired by theoretical physics. So with that, I would like to wrap up. I can now talk about machine learning applications in physics, and let me just thank everyone for your attention, and especially listening to a talk that was kind of probably out of your scope. And thanks again for inviting me.